This is a review of the June 2014 Regents Chemistry exam. I am going to review all the questions of the Part B2 and Part C, the free response section if you want to think of it that way, of the Regents Chemistry test of June 2014. So let's get started. Right now you're looking at the answer booklet where your answers would go on to, since this is a free response section. It's open-ended and you're going to put these responses. So we're starting with 51. So before we answer 51, let's go to the test. Number 51, draw a Lewis electron dot diagram for a molecule of bromomethane. All right, so the organic compound they gave me was CH3Br, and I'm going to draw this Lewis dot diagram. I'm going to start with my central atom, which I know is going to be my carbon because it can have the most bonds. It has 4 valence electrons. Now, if I wasn't sure about that, I can go to the periodic table. So I find my carbon, who is 2-4. That's its configuration. That means it has 4 electrons in its outermost electron, and it needs 4 more to have the most stable electron configuration. So it has 4 valence. Also, to get valence electrons, you can look at the last number in each of these groups here, or the first number when it only has one integer. So yeah, the valence electron here is 4. The other chemical, bromide, is a halogen. It's in group 17, and it would have 7. Notice its number down here is 7, the last outermost shell that's not filled. So it has 7 valence electrons. And the hydrogen, if you're not aware, okay, going on the other end of the spectrum here to find the hydrogen, it has, of course, 1 valence electron, having only 1 electron overall, and needs 1 more to fill its energy level. So it has 1 valence. Knowing the valence electrons, that's where we start, where we write a Lewis dot diagram. So I have to put out all my valence electrons. Carbon has the 4. As you can probably guess, we're going to have an H who brings 1. And you certainly don't have to color code this in the real test, but I'm just kind of showing you where this comes from. And I put 3 H's around, and we have a bromide. And where you put the bromide is inconsequential, does not matter, okay, as long as it's on the carbon, because carbon makes 4 bonds, going to make 1 bond with the hydrogen, each of the individual hydrogens here, so 3 bonds overall. And then we're going to make 1 bond with the bromide. Now, bromide has 7 valence electrons as well. And you know, it's a nice match. It's a nice fit. The bromide has 7. It shares with the carbons 1 to make a bond here. And each hydrogen brings 1 to the table. And then they each share their valence electrons. And if you notice, everyone has their stable number. Hydrogen has its 2 electrons by sharing to feel like it's like helium. Okay, carbon, by sharing electrons with the hydrogens and the bromide, feel like they have 8. And the bromide, by sharing 1 with its carbon and sharing carbons, feels like it has 8 as well. So you don't need the circles, but that kind of shows you that each carbon, by sharing its electrons, its valence electrons, has reached its stable number, or its stable configuration. So this is an appropriate Lewis dot diagram. You certainly could write it another way. You should be aware that a bond is a pair of electrons. So I could have also written the Lewis dot diagram this way, showing a dash representing a pair. You should know a pair of electrons is a bond, and then of course bonded to the Br. But if you left it the way that I just did it here, you'd be wrong. You have to show lone pairs. If you're going to put dashes for the individual bonds, you have to draw the lone pairs for elements that have them. Nobody has them except for the bromide, so you had to show the lone pairs if you drew it this way. But either way is fine. 52. Number 52 states, explain in terms of atomic structure why group 18 elements on the periodic table rarely form compounds. You really need to pay particular attention to how they want you to answer the question. They're saying in terms of atomic structure. Now, when we say in terms of atomic structure, we're talking about the atom. And inside the atom, of course, you've got the protons and the neutrons in the nucleus, and electrons, of course, on the outside of the shells. I don't want to write circles or not necessarily in the Bohr model. So we have electrons on the outside and of course protons on the inside. So in terms of atomic structure, why do they rarely form compounds? Now you should know that group 18 are the noble gases, and noble gases are very, very stable, and stable means they have low energy. They have low energy, and that also means they don't do anything because they need energy to change their position. Now you should be aware that the group 18 elements, the noble gases, why are they stable? Let's go to the periodic table. So here are our noble gases in group 18. All right? And these guys are special because they have very little reactivity. Some of them have absolutely none, and there is a little bit of reactivity in truth with some of the ones down here. But generally speaking, they don't do very much. They don't achieve and make bonds with atoms because they have stable electron configuration. Helium in the first energy level, the first energy shell, has a maximum of 2 electrons. Its configuration of 2 means it has already attained the lowest energy position you can have by having 2 electrons. Neon, if you can see, and let's zoom in here, get up close and personal, and we zoom in here and we see that neon has 2-8. Now 2-8 means it fills its first and its second. It has that stable, what we say, octet. So it's filling its energy level. So there's something to be said when electrons, when you have a filled energy shell, that's a configuration that's low energy. So noble gases, for the most part, have filled octets. They have that 8 in their outermost shell that makes them have very stable, low energy electron configurations. There's something about that. So that's where you're going with this answer, because we're talking about atomic structure. They want you to answer in terms of atomic structure. So let's put an answer down. So I wrote, noble gases have stable electron configurations. There's many ways you could say this. You could say these group 18 elements are not very reactive because of stable electron configurations, because they have the maximum amount of electrons in their valence shell. You could say that their valence shells are completely filled. Oh, that's a stretch for some of them, but you could say that. And you can also say they have a stable octet, but careful with that one. Remember, helium doesn't have to have a stable octet. Helium just has a filled valence shell. Remember, helium in the first shell only holds 2 electrons. Okay, but the bottom line is that what you're really after here is stable electron configurations. Okay, which means that they have the highest amount of electrons in that shell for that period. Number 53, explain in terms of electrons. Very important you pick up on exactly how you want to answer the question. So in terms of electrons, why the radius of a potassium atom, all right, now again, a potassium atom, you say atom, I say neutral, atom, neutral. Atoms are neutral because their protons equal their electrons. It's important when you understand what's happening here. Is larger than the radius of a potassium ion. What charge is a potassium ion? Ion means you become positive or negative. Well, you should know that potassium is a metal and it likes to become positively charged. So this problem is about you recognizing the fact that the metal becomes positive. It's important you know that, and got smaller. Now, if you weren't aware of that, you could look on the periodic table, and you can see that it likes to become +1. Okay, so metals all become positive. There's nothing new there. By knowing potassium's a metal, metals lose electrons. They hold on to them loosely. It's what makes them a metal. They're big radii. Any case, going back to the question, now that we know that it became positive, just to make sure, and knowing that metals lose electrons, which by the way is called oxidation. Standalone metals like to oxidize, right? Standalone metals can only become positive. So you had to lose an electron here. If you wanted to write a half reaction, you go +1e negative, right? You'd lose an electron. But the bottom line here is if you're losing an electron in the process, the number of protons is staying constant because it's still potassium. What makes potassium? Potassium is 19 protons. Okay? That is what makes potassium special. No other atom has 19 protons. So potassium has 19 protons, and that's going to stay constant no matter if it becomes positive or not. The idea here is that if it's K, the symbol represents that 19 protons. Understanding that the protons weren't gained or lost, it had to do with electrons, and I know I'm just kind of over teaching this, but the idea here is if you lose electrons, this one has one less electron. Therefore, its protons outnumber its electrons. So explain in terms of electrons when the radius of the potassium atom is larger than the radius of potassium ion. Well, the potassium atom has what? One more electron. The potassium ion has one less, and that would be enough to explain. All right, because if you lose electrons, you're going to have a smaller radius. And I always tell my students, remember this. If you lose weight, you get smaller. If you gain weight, you get bigger. Now, of course, the idea behind this, if you have one less electron than the protons, okay, the protons are going to pull you in. So this is atomic number 19. This is atomic number 19. This is 19 protons and 19 electrons. This is 19 protons and 18 electrons, right? So this atom here has the same number of electrons as protons. Here you lost an electron. So the protons outnumber the electrons, and if that's the case, the remaining protons, or the protons still there, pull in the electrons a little smaller if the protons outnumber. Bottom line, you lose weight, lose electrons, you get smaller. Let's write the answer. So I said a potassium atom has one more electron than a potassium ion. That's it. They love to ask about this. This is definitely a topic that comes up. If the ion loses an electron, then that's the reason why it got small. The reason why the atom is bigger, it has one more electron. Okay? And remember, they asked you to write your answer in terms of the number or about the electrons. So make sure we follow that rule, and of course we did. The question, if you remember, stated in terms of electrons. You could also say the potassium atom has one more electron shell than the potassium ion. Say the potassium being the K atom being 2-8-8-1, and the K plus ion, cation, is 2-8-8. You could say by having the one more electron, it has what? More shells of electrons, and that's why it's bigger. And the K plus, okay, having one less electron, has less shells of electrons, and that's why it's smaller. So another way to think about it. All right, number 54. So number 54 states, identify the type of bonding in solid potassium. So if you've got potassium, if you have pure potassium, which is pretty reactive, you would never write the chemical formula potassium and count how many atoms. You would just say K solid. And how does this metal stick together? Well, the metals are bonding with themselves, and anytime you got metals bond with themselves, we call this metallic bonding. So to identify metallic bonding, you probably learn that all you got to do is see the chemical symbol, because you would never count how many atoms bonded. Like pure copper wire, the chemical formula would be Cu solid. So you had to recognize the fact that if you've got solid potassium, that means metal atoms are bonding with metal atoms, and that's metallic bonding. That's where you have that sea of mobile electrons. So number 54 is metallic bonding. Number 55. Number 55 states, determine the molarity of the solution. You know, I would always tell my students, go right to the question before you see a blurb. See, in these areas, you're going to see maybe a little blurb, okay, about some information regarding the question. A lot of times this information is a lot more than you need for the problem. So I always say read the question first to see what they're after, and then go pick out what you need and not be intimidated by all the information they're giving you. That seems to work for a lot of my students. So molarity, they want the molarity of the solution. Now molarity is a concentration term. And if you forget, there's a place to look, table T. Let's do it. So here's table T, and we'll just scroll down to find concentration, and we see molarity right here. And molarity is equal to moles of the solute over the liter of solution. So that's the formula we need. So moles of solute over liter of the entire solution. Now, solute is the substance that gets dissolved. So let's go back into the question. We have a 2.5 liter solution. So they just told us the solution. And we have 1.25 moles of the dissolved sodium chloride. That's the stuff that gets dissolved, and that's the solute. The solvent is the water. The solute is what gets dissolved. So we have our numbers. So all we got to do here is take our 1.25 moles right up top and divide by our liters. Pretty straightforward. Let's do that in the answer booklet. Now, some questions are going to ask for the work. Okay, this one's looking directly for the answer, but it's good practice to show the work if you forget that you have to do that. So molarity is equal to moles of solute over liter of solution. All right, so in the problem, okay, they said that we had 1.25 moles of dissolved sodium chloride. So that goes right up here, 1.25 moles of dissolved solute. And they also told you have 2.50 liters of aqueous solution. Okay, that's the entire solution, so 2.5 liters. All you've got to do now is plug that into your handy dandy calculator. So let's do that. 1.25 divided by 2.5 liters, and I get 0.5. 0.5. Now, I probably want to use 2 sig figs, and again, they're not asking for them, but just good practice. The least number of sig figs is 2 here, so 0.50. So 0.50 molar. Now, if you were not to use 0.50, you'd 0.5 or 0.500 or any combination, they would still accept it because they have to tell you they want the proper number of sig figs. They weren't looking for the work, but it's good practice to show it because there'll be some questions possibly where they're looking just for the work. Okay, so here we go with the next question, number 56. Number 56, compare the freezing point of this solution to the freezing point of a solution containing 0.7 moles of sodium chloride per 2.5 liters of solution. Okay, so what they want to do is compare the freezing point of the solution that we just determined from the last question, where we had 1.25 moles of dissolved sodium chloride in 2.5 moles of water, liters of water, sorry. Now that, of course, magically equaled 0.5 molar solution. So we want to compare the freezing point of this solution, they're talking about what we just talked about here, to the solution that contains 0.7 moles, 0.75 moles. So in this new solution, we'd have to figure out who is more highly concentrated. Okay, it's still NaCl, so we don't have to consider whether or not there are salts that dissociate more. So it's the same compound. You notice it's the same amount of water, right? So if you notice, we added 1.27 moles of sodium chloride to 2.5 liters. Here they're adding 0.75 moles to the same amount of water. So if you were to calculate the molarity for 56, the molarity is going to be lower. The concentration has to be lower because we have what? Less moles of sodium chloride than the moles of sodium chloride in the above solution they're talking about. So compared to the freezing point of this solution that has what? More sodium chloride, the freezing point of a solution that has less sodium chloride, okay, would have what kind of freezing point? Now we've just established that clearly this has a lower molarity than what we just calculated for. But now they're asking about something about colligative properties. And we should recognize the fact that if you have more solute particles dissolved, okay, and I'll write them as these blue dots, the harder it is for water to freeze. Now, I don't want to spend a long time talking about that, which is, something I usually do, but if I have some ice in the bottom, if I have some ice, I guess, stacked up, all right, the ice is going to try to melt, all right, and melting isn't the problem, it's the refreezing that has the issue. What you should know is it's harder for the water molecules to refreeze if there's solute particles getting in the way. So you need a colder temperature to overcome these particles to freeze. And that's why we call it freezing point depression. The freezing point gets lowered as you add more solute particles. So because we're comparing the freezing point of a solution that is higher than the freezing point of this solution, we would say the freezing point of the higher solution would be lowered. Okay, I know it's kind of confusing, but the higher the concentration, the more stuff in solution, the lower the freezing point. So let's look at the question again. Compare the freezing point of this solution to the freezing point of the lowered solution. The freezing point of the higher concentration will be lower because the more stuff you add into the water, the harder it is for the water to get to the surface of the crystal and freeze. You need a colder temperature, okay, to do that. And I always tell my students to remember freezing point depression by doing the 2 thumbs up signal. Here's the thumb, okay, and here's I guess my fingers, and then I have another thumb coming down, and I guess I have my hand on the other side, and I do that. I show my kids that if you do the thumbs up and thumbs down, the higher temperature rises, that's boiling point elevation, and the lower temperature always drops, freezing point depression in this case. So let's go write our answer. So I said the solution with 1.25 moles, that was the solution, the original solution, which is the 0.5 molar solution that we just calculated for in 55, has a lower freezing point. That's all you needed to say. Now you could say it's lower than the first one, okay, the solution, this solution has a lower freezing point, but I would be pay particular attention to what you're responding to. I would tell the reader, the person reading and grading your Regents, what you're talking about. I would not make vague comments. Hey, the solution decreased or increased. Tell them exactly what you mean. The solution that had the higher concentration has a lower freezing point. Just tell them that. Now, you certainly could say this the other way. The solution with the lower concentration has a higher freezing point because it didn't drop as much. You can say it that way too, but pay particular attention to how you answer this. Do not get vague, and you start getting vague and not specific enough, you may lose points, okay? So tell them exactly. The solution, which solution? The one that is more concentrated, that's the one I'm talking about, has a lower freezing point. And you could explain it the other way, but again, it's very good to use to be more specific. Okay, number 57. Okay, so typical Regents question, they have a little blurb here, and then they have a reaction and stuff going on, and you may read this entirely and say, oh my gosh, what are they talking about? It doesn't matter. I suggest you go right to the problem so you don't get turned off about what information you may understand or not understand. Go to the problem, then go back and see what you need for your problem. You'd be surprised. Here it is. Write the empirical formula for glucose. Now you say, okay, I know what the empirical formula is. If you didn't, then that's a problem. But empirical means lowest ratio. Okay, you saw this, the lowest ratio of atoms in the formula. Okay, now you may not know what glucose is, so you have to go back into the problem. Oh, it says a sample of glucose. So telling me glucose is this. All right, so the lowest ratio, I mean it's a 6 to 12 to 6. If I reduce by the lowest by 6 all the way through, I get a CH2O. And it's just that simple. I'm looking for the lowest whole number ratio. So the factor that 6, 12, and 6 can all be divided by is 6. So they still get whole numbers, a 1 to 2 to 1 ratio. Okay, number 57, let's go put that down on our answer booklet. A relatively easy question, 57, the lowest ratio. Number 58. Okay, number 58, use the axis in your answer booklet. Complete the potential energy curve for the reaction of glucose with oxygen. Okay, so I've got glucose and I've got oxygen, and they want to complete a potential energy curve. If you remember that, they're going to be either exothermic, which means you're starting high with energy and your products have low energy, or they're going to be endothermic, starting low with energy, very stable, and ending up with high. So to know if you're either drawing a potential energy curve that's going down, that means your delta H is going down, which means it's negative, which is for exo, or if the difference of where you start, which is delta H, is going up, delta H is positive, okay? Again, delta H is the difference of where you start and finish. In this case, we're going down exothermic. This one's going up, so it's positive. This one, of course, is endo. This one is exo. So we have to figure out in our reaction if it's an exothermic or endothermic reaction. And what tells us, the key to the entire thing, is where the energy is listed. It's put on what we say the product side. Okay, the right side is the product side. And if you're producing energy, energy is going to escape and leave. And if energy is leaving, that means your energy is going to what? Drop and be a negative delta H. If your energy was on the reactant side, you means you would need that energy to be absorbed or consumed to go up in energy. That's the key. If the energy is on the product side, it is exo. If the energy was in the reactant side, it'd be endo. So let's go draw our exothermic curve because the energy is in the product side. Okay, so we've established that the reaction of glucose, a sugar, with oxygen gives off energy. Energy's in the what? Product side. So therefore energy is what? Exiting. It's exothermic. Okay, so we know that our potential energy curve is going to go down, and that your reactants should have, your products, these are your products, should have less energy than your reactants because energy was released. To get full credit, you needed to show that the product's energy was lower, and you needed to have some kind of an activation barrier. You needed this hump here to show that there is some kind of barrier that prevents the reaction from just becoming products and just burning and reacting automatically. So that's this little hump here that you measure the activation energy from that. So you needed to have this peak here that's higher than both, but the products had to be lower. Number 59. So number 59, identify the class. And again, you get a little blurb here. And again, you want to read it, go ahead. But I suggest you read the question first to see exactly what they're asking from this blurb. It's the way that I tell my kids, if your teacher tells you otherwise, you do what you think is best. But I really believe, go look at this question first before you try to read through this information that you do not know if it's important yet. Identify the class of organic compounds, types of organic compounds, which ethanol belongs. All right, now if you didn't know what ethanol is, you probably could figure it out from your table R, but they were very nice to give it to you, is C2H5OH. So what is ethanol? What kind of class does it belong to? Well, you can look at a couple of different reference tables to do that, but if you want to draw this out, you can have 2 carbons. You're going to have 5 H's, and then you're going to have an OH. If you want to put the H's in, you can, and I'm just drawing this so you can see a couple of different ways you can answer this that are acceptable. The best way to think about this is that when you have a hydrocarbon chain and you have a group of atoms that bond to it a particular way, we call these functional groups. So functional groups, and this OH group called a hydroxyl group makes this entire compound something called an alcohol. Now if you weren't sure about that, you can go to table R to see that. Let's do that. So we can see that when you have an OH attached to a carbon chain, and here's an example that you can look in table R, that functional group, or that class of compounds, is something called an alcohol. All right? And alcohols have a general formula if you need to use that. This R means the rest of a hydrocarbon. There's the R right here. And then you have the OH attached to that hydrocarbon, and that's called an alcohol. So that's just recognition from table R if you didn't know ethanol was the alcohol in, let's say, wine, liquor, and beer. So we put alcohol. Now, they call an OH group a hydroxyl group. So you could say a hydroxyl or monohydroxyl alcohol. You could also say, and I believe this would work too, is that because it was an ethanol, okay, I believe that you could have called this an alkane. Now, I know alkanes are hydrocarbons, but they are single bonded between the carbons, so some people consider alkanes to be fine here too. The best answer that they're after was, could you identify from table R that it was an alcohol? And I would say definitely the one you really should be able to identify. Okay, number 60. Number 60, a liquid boils when the vapor pressure of the liquid equals the atmospheric pressure on the surface of the liquid. Based on table H, what is the boiling point of ethanol at standard pressure? Well, it was really nice of them to give you the first sentence because that's something you should know. You should know that when something is boiling, okay, it's because the liquid molecules, when they escape their intermolecular forces of attraction and get to the surface, if they have enough energy to do so, create a pressure upward. And if that pressure upward, which is called vapor pressure, equals the atmospheric pressure due to the gas molecules that are already in the atmosphere, we have something called maximum evaporation, which is boiling. So we know that if I increase the pressure, we would need more vapor pressure to equal that and boil. And we also know, as you probably may have seen, hopefully, that if you were to lower the pressure, like in a vacuum chamber, then you would need less arrows up or less vapor pressure to boil, and therefore boiling occurs at a lower temperature. Any case, the biggest factor that is in charge of boiling, or the most important factor, is the atmospheric pressure. But they told you that the vapor pressure has to match the atmospheric pressure. All right, so they're giving that away, and then they're saying, what's the boiling point? In table H, they're also telling you where to look for ethanol. So let's go to table H and see what temperature the vapor pressure of ethanol equals the standard pressure. So here is table H, and we need to know that ethanol is the second liquid, second line here, and we can see that the ethanol, as temperature increases, the amount of vapor pressure, or the force of the liquid molecules escaping at the surface, steadily increases. When that pressure equals the atmospheric pressure, which in this case is standard at this table, we have boiling. So what temperature is the liquid when its vapor pressure equals this dotted line? And that's what this question is about. And we would say something close to, well, if this is 75, this would be what, 80, 85, 90, 95. So you can see that's going by 5, so it's a little less. If you said 70, oh, I'm sorry, yeah, 79 or 78, those are all good guesses. I'm going to go with 79. Okay, it's just before that 80. Now, so I said 79, and the state would take anything from 78 to 80. Okay, so they give you a little range, a little breather there if you didn't, or you don't have the same precision, okay, as maybe I do or someone else, or however, you have to have some, yeah, I hate that. So I write 79 degrees, and that's my best guess. The state gives you a range from 78 to 80 that they accepted, and that's pretty fair because you can't read individual integers. You are making a guesstimate. So they give you a little bit of breathing room from about 78 to 80 here, okay, and it's coming from the state, what they accepted for this answer. So 79 is pretty fair. If you got 78, even gave you 80. 80 to me is a little bit, a very generous answer because it clearly is before that number. But listen, hey, take it where you can. All right, number 61. So in number 61, compare the intermolecular forces. These are not bonds. These are the attractive forces between the molecules of the two substances at STP. So we have to go back into our blurb, and the two substances are ethane, which has a what? Very low boiling point, and our ethanol, which we just found out to have a boiling point of what? 79. So we have 79 approximately degrees Celsius for our ethanol, and we have negative 89, a very large difference in boiling point, much lower for the ethane, which we should know as a hydrocarbon with single bonds. Now, compare the intermolecular forces. Well, you should understand at this point that if I have a higher boiling point with ethanol, much higher, that must mean it's very, very difficult for the ethanol to overcome its attractive forces than it does for the ethane. If the ethane boils at a lower temperature, as they're telling us, it must mean that ethane molecules can overcome the attractive forces of other ethane molecules much, much easier than ethanol can if it's able to what? Boil and evaporate and create a vapor pressure. So we would say that clearly the lower boiling point, this is important, lower the boiling point, okay, the weaker the attractive forces. And this is something we talked about at length when we talked about vapors, attractive forces, okay, or IMFs, intermolecular forces of attraction. Also, if you remember ethanol has an H attached to a very electronegative atom. Ethanol can H bond, which is one of the strongest attractive forces, and that explains why it resists evaporation more than ethanol. It takes a lot more energy. So many ways to explain this, but you had to realize a lower boiling point means the ethane's molecules have weaker attractive forces and they produce a higher vapor pressure for the same temperature. Okay, remember we had liquid nitrogen, if you are lucky to see that. Liquid nitrogen, its boiling point is somewhere near negative 200 degrees Celsius. With that lower boiling point, you would say, wow, okay, that thing really has weak attractive forces. Okay, water boils at 100. So water resists evaporation and boiling compared to ethanol and ethane because they have even stronger intermolecular forces of attraction. Okay, so lower the boiling point, the weaker the attractive forces, and of course, higher the boiling point, the more energy, okay, you need to make them boil because they're holding on strong. It should be something that you definitely understand here. It's an important concept. So let's go write the answer. Now, before you do so, I couldn't help myself going back to this table, realize we have 4 lines, okay? And you look at this, let's call it, for this point in time, we'll call it liquid A. This liquid A, okay, has the highest vapor pressure at any temperature. So if you take, let's say, 50 degrees and look at these 3 liquids, you can see that this liquid, okay, has a much higher vapor pressure. What does that mean? That means it must have what kind of intermolecular forces of attraction? Weak. It's able to do what? It's able to escape each other's attractive forces and evaporate and cause a vapor pressure. And these other liquids, like liquid B over here, resist evaporation like water because they have a much lower vapor pressure. And it makes sense they would need a lot more energy to what? Boil than something that evaporates very easily. So it is very logical. So all you really needed to say here was ethane has weaker intermolecular forces than ethanol. Okay, that's all you need to say, and it's an important concept. Notice what I did in my explanation, which is a good practice. I talked about both of them. I wasn't vague. If I said, hey, if I just said it has weaker intermolecular forces, I'm really on the ledge of getting something wrong because you should be specific in who you're talking about. Ethane has weaker than this chemical. Be specific. Don't be vague. Don't give the greater an opportunity to mark it wrong because you weren't specific enough. Okay, make sure you're correct in your writing. But ethane with the lower what? Boiling point, okay, boils it doesn't need as much energy to boil because it holds on weakly. Okay, number 62. So 62 has a nice voltaic cell in front of me. I've got myself a battery. And how do I know? Because I can see myself with a voltmeter measuring the voltage. I see a salt bridge that only a battery needs. Okay, so very important there. And now the question states, number 62, identify the subatomic particles. Subatomic particles are smaller than an atom. Well, they make up the atom. Those are the protons who are in the nucleus, who are positively charged. Those are the neutrons, who are also in the nucleus, that have no charge. And of course, the electrons outside the nucleus, okay, that are in those orbitals and those electron shells. These are the subatomic particles, and they want to know which one flows through the wire. Okay, well, it's going to be the electrons. Electrons create the electricity, the charge differential. So it's the electrons that flow. Some people would argue it's the charge, but we're keeping this simplistic at this level. So if you're not really sure why, well, the one who oxidizes, zinc, standalone metal, it's better in oxidizing than the iron. Besides, the reaction is showing me the standalone metal can only oxidize. Its number is doing what? Its number is going up because it's losing electrons. So it's oxidizing. These two electrons are sort of pushed through this circuit here. And the iron plus 3, whose charge is going what? Down, plus 3 to 0, is essentially what? Pulling them. The iron plus 3 comes here and it plates onto this as it becomes Fe plus 3 electrons to make the solid iron in the 0 phase. So eat this question up. We should really like this one. We're making solid iron here. Remember, any metal who has a 0 charge is a solid with the exception of mercury, but we're not going to see that in these batteries. So a solid zinc becomes aqueous, and the iron plus 3 in solution becomes a solid. In any case, it's the electrons. And I guess this question was more about, do you understand that redox reactions are passing electrons around? The reason why we have to balance mass and charge is because of the flow of electrons from the one who oxidizes to one who reduces. Okay, 62. Next question, 63. So 63 states, balance the equation in your answer booklet for the redox reaction that occurs in this cell using the smallest whole number coefficients. So I've got the reaction right here, no need to go back to the question, and I need to balance it. Okay, now I can do this two ways. I'm going to do it the half reaction way first. Okay, I'm going to take my zinc 0, standalone. I know this is plus 3, this is plus 2, and this other element is a standalone. Anytime you have an element by itself, it is neutral. Atoms are neutral. You say atom, I say neutral. Neutral. Okay, thanks for yelling that. Now, let's write our half reactions. So zinc 0 on the reactant side becomes zinc plus 2 on the product side. You can see there's a difference of two numbers here, 0 to plus 2, and that's because 2 electrons were given off. We put the 2 electrons on the product side because a negative 2, each electron's negative 1, and a plus 2 is 0. This side is 0. Both sides of a half reaction have to have the same charge. Then I take iron plus 3, which is a reactant, and I do what with it? I make it the product, which is Fe0. Now, this charge is not balanced. The plus 3 and a 0 do not have the same charge. So I need to add 3 electrons so that both sides of my half reaction have the same charge. So I add 3 electrons right here. Because a negative 3 and a plus 3 is 0, this side is 0. Both sides of a half reaction have to have the same charge. So my half reactions are balanced with themselves, but not with each other in terms of the 2 half reactions. So we're going to have to start thinking about how can I balance these electrons. You can see that 3 electrons are absorbed or used in the reduction, and only 2 are released in the oxidation. So we have to balance this. Once you balance the electrons, which is really balancing the charge, you balance the overall reaction. So what's a common factor of 3 and 2? Of course, that is 6. So I'm going to multiply and distribute 3 right across everything here to give me 6 electrons. So 3 times 1 is 3, 3 times 1 is 3, 3 times 2 is 6. That gives me 6 electrons. Now to get 6 electrons over here, I multiply everything by 2. 2 times 1 is 2, 2 times 3 is 6, and then 2 times 1 is 2. And now you can see that my electrons, I have 6 electrons on this side, which I can cancel, and I have 6 electrons. We just balanced our charge. Same number of electrons are being used in reduction as the same numbers are being used and given off in oxidation. We can cancel them off because they're on both sides of the arrow. I have just balanced my charge, so now I have just automatically balanced my reaction. 3 is in front here, 2 is in front here, 2 is in front for the Fe, and then 3 right here. All right, now if you don't trust yourself, you can check to make sure that both sides of this redox reaction has the same charge. 3 times 0 is 0, plus 2 times plus 3 is plus 6. 2 times 0 is 0, plus 3 times 2 is plus 6. Both sides have the same charge. Now, could you have done this another way? If you didn't like the half reaction way, yes. Okay, so let me write it. If I had zinc here, zinc 0, then I had plus Fe plus 3, goes to what? It goes to zinc plus 2, and iron, 0. How could I have done this without half reactions? I know some teachers are like shivering now, but I could have used the charges. Notice this side is plus 3. This side is plus 2. Not going to work out, not going to happen. So we have to make them have the same charge, which is the same thing as balancing the electrons. So party people, to get plus, it's a common factor of 3 and 2, 6. So I want plus 6 on this side. I want plus 6 on this side. So how can I get plus 6? Oh, this is plus 3, so put a 2 in front. Now, I'm balancing the charge. I have to also balance the mass. I put a 2 here as well. Okay, why? Because 2 irons have to equal 2 irons. I can't just forget about law of conservation of mass. Now, how do I get plus 6 on the other side? Well, this is plus 2. To get plus 6, I put a 3 in front. And I have to balance the zincs. 3 zincs on this side, 3 on this side, and you get the same result. So it doesn't matter which way you work. That should be hopefully helpful to you. Number 64. So 64 states, identify one metal from table J that's more easily oxidized than zinc. So if you think about an activity series, which metals are more reactive? Who gets oxidized better than zinc? So let's go to table J. So here we are with table J. It's an activity series for metals and nonmetals. So we're talking about metals, we're going to live on this side. The most active metals are on top, and metals, you should know, lose electrons. They get oxidized. That's what they do. Metals become positive. Metals never become negative. You can't find an oxidation of any metal who becomes negative. So metals lose electrons. They oxidize. So this is a list of who oxidizes the best. Now, if we were living over here with nonmetals, nonmetals gain electrons. They're the smaller ones. They get reduced. So this is a list of who reduces the best. Okay, but we're living on the left side because we have what? We have metals. So who's better than oxidizing than zinc? All right, well, here's my zinc. And I can pick any metal who's better than zinc, and that would be any metal above that. So you could pick any metal you want that's above zinc. Of course, if you remember our lab, okay, our activity series lab, we had calcium, and clearly that was the most reactive of all the metals. Magnesium was second, zinc was third with our lab, but maybe you did a very similar lab in your class, or you watched some videos. Maybe you saw someone dropping sodium in water, okay, or doing that. And look where sodium is, okay? Sodium's about the same place. Strontium, barium, potassium. In any case, these are all very reactive metals that you would build nothing from because they react too well with the oxygen or the water in the environment. In any case, so any metal above zinc would work if you understand how table J works. So I put calcium or any metal above zinc. Okay, number 65. 65, explain in terms of zinc atoms and zinc ions. They're asking you to explain in a certain way. Don't be vague. Explain how they want you to. Why the mass of the zinc electrode decreases as the cell operates. So in terms of the atoms and the ions, you have to match both of them. Okay, the mass of the zinc electrode is decreasing because zinc is the anode, right? Zinc is the place of oxidation. Look at your half reactions. Look at the reactions they gave you. Okay, zinc is the 0. Now, if you didn't have this reaction, you go to table J and see that zinc is better in oxidizing than the iron electrode, which tells you that this is the anode, the place of oxidation. But zinc 0 is going to zinc plus 2. I wrote the half reaction right here. So in terms of the zinc and the zinc ions, you would say at the zinc electrode, zinc solid gets oxidized into zinc plus 2 ions. Zinc becomes aqueous ions, and that's why the mass decreases. As a piece of zinc solid gives off 2 electrons, it makes zinc plus 2 ions. So this electrode gets smaller as we produce more and more zinc, the solid metal. And that's why I always put a square around the metal that is 0 to remind you that this is a solid. So the zinc metal, okay, solid 0 becomes aqueous ions that go into solution as the cell operates. Now there's many ways to say this, but the zinc atoms, the solid, okay, neutral atoms get oxidized and become zinc ions. When they get oxidized, they lose electrons, they lose negatives, and they become zinc ions that get dissolved in solution. All right, so many ways to say that. Zinc atoms become zinc plus 2. Zinc 0 becomes zinc plus 2. You know, the atoms become ions. There's so many different ways to say it, but gosh darn it, the solid zinc, who is an atom, loses electrons and becomes charged. And that charged ion, it can now interact with the water and get dissolved. So the mass of the solid zinc decreases. So here we go with part C of the test. Now part C of the test can be a little bit intimidating because they're going to give you a little bit more information, or the blurbs that we've been seeing in this free response section of the Regents chemistry test is going to get bigger here. So it looks a little intimidating sometimes because they're going to give you some information that you may or may not recognize. My suggestion is that you go right to the problem to see what they're after first, understanding that when you get to this part of the test, you're a bit tired. And if you start reading information that may or may not be part of the question, it may make you think that you don't know what you're looking at. It may give you some anxiety. I have a lot of students over the years who look at this part and they get anxious and they're like, what am I reading? I don't know this. And then when they get to the questions, they don't do very well because they think they should understand everything in front of them. So I would like for you guys to go to the questions first. That's my advice here. Not sure what your teacher says. And then go back into the problem. I really think from my experience that that's very helpful. Any case, so we've got these models of an atom, and it says a student compares some models of the atom. These models are listed below in order from top to bottom in terms of development. So you could read all of this, but I suggest you go right to the question, because as you're going to find, the answers they're looking for are much simpler than the information they present to you. So this is a wealth of information that could make you anxious and have a little bit of anxiety, or even, afraid to say that I don't know all this. You don't have to know much. The things that you've been knowing all year is all they're asking. So number 66, state the model at first included electrons as subatomic particles. Okay, now we have a way, and now we have some hints of what they're looking for. So I'm looking for a model which is listed on the left that first included electrons. Now, if you don't know this off the top of your head, then you go in. So we've got matter conserved, cathode rays. I'm reading atoms are hard individual spheres. Atoms have small negatively charged particles. That's the hint right there. So they're looking for you to understand that the negatively charged particles that you have been talking about all year, okay, are electrons. So the hint here is that we're talking about electrons. Now you might remember the Thomson model. He discovered electrons using cathode ray tubes and moving those rays with a certain amount of energy and measuring that energy. Any case, so we're talking about electrons here, negatively charged particles. That's what you needed to understand. So clearly, we're looking for the Thomson model. It's only what state the model that included electrons. Electrons are, of course, negative. Now, you could go to table O to see that if you look up something called a beta particle, which is an electron that comes out of a nucleus. And you can see from table O, they would give you a 0, an E, and a -1, meaning the mass of an electron is considered to be 0, considering its small size, and then its charge is -1. But you probably know that electrons are negatively charged from your redox review or part of your studies. Okay, so 66. So as simple as writing the Thomson model, some of you guys might remember that the Thomson model was the plum pudding model where you had an atom and the electrons were in this atom like plums in plum pudding, just in the atom haphazardly, meaning the idea that electrons are somehow just in the atom with no real organization like plums in plum pudding. So that's something else you could have written too if you remembered that. So number 67, state one conclusion about the internal structure of the atom that resulted from the gold foil experiment. Yeah, it's Rutherford's gold foil experiment that you should know for this test already, but they outlined it here in this model. So what about the internal structure? They want they want a conclusion, okay, which in some, this is to me very odd. In this test, they give you the conclusion, which is listed right here. So it's, and some of the other tests you probably have taken, this is conclusions you have to come up with, but right here in this information, they tell you that the conclusion for the Rutherford model, which is the gold foil experiment, you can just read, an atom is mostly empty space, has a small, dense, positively charged nucleus. Okay, so it's just reading comprehension right here. No reason to get that wrong. Okay, so let's go to the answer booklet. So I write, of course, the atom is mostly empty space, and that'd be good enough. You could also say it has a small, dense nucleus, which is the other part of the conclusion. It's positively charged. It has a nucleus, okay? All of that, which was basically given to you right in the chart. They just wanted you to take it right out of the chart. To me, this is a reading comprehension. Okay, very, very strange to me that to have something that easy, but you know, I guess you can take it if they give it to you. Number 68. So number 68, using the conclusion, you have to read particularly well here. What are they asking? How do they want you to answer the question? Using the conclusion from the Rutherford model. Okay, well, our conclusion was that the atom is mostly empty space with a small, dense, positively charged nucleus. All right, so using that conclusion that we just read and they gave it to us, identify the charged subatomic particle that's located in the nucleus. So, okay, what is this positively charged, okay, why is a nucleus positively charged? Okay, so what's the particle in the nucleus that's positively charged? And of course, that's the proton. And if you were to go to table O again, all right, you would see the proton sometimes is written like this, an H, a hydrogen, 1 over 1. It has a charge of +1, and it has a mass of 1. Table O can tell you that, but I don't think you needed to know that what's in the nucleus is positive at this point. It's the proton. So I write proton, And certainly you could write symbols that represent a proton. A P would be acceptable, P plus, P11, H11, H plus, all symbols we use for protons. These, of course, come from table O to show the mass number here and the charge number here. So number 69. Number 69, state one way in which the Bohr model agrees with the Thomson model. Okay, so the Bohr model, as you probably already know, we have unique spectral lines are emitted by gaseous elements, okay, that come from electrons jumping back to their stable states. Packets of energy absorbed by emitted by atoms when the electron changes shells. We learned about that, easy for me to say. Okay, now, how does the Bohr model and the Thomson model have any kind of parallels? Well, Thomson was about negatively charged particles, and Bohr model was about electrons changing shells. So what's the similarity here? The similarity here is we got negatively charged particles and we have electrons. So since Thomson discovered the electron and Bohr uses electrons changing shells, okay, certainly they would have to have some parallels in the fact that they're both using electrons. So I wrote for number 69, atoms have electrons. I mean, it's just that simple. Atoms have electrons. Both of those what? Both of those questions ask for one way in which Bohr model agrees with the Thomson model. Both of them use electrons. They have electrons. And you could say they both have small negatively charged particles, which are the electrons. Or you could say, listen, atoms are neutral because both of them talk about atoms having these electrical small negatively charged particles. And if you're talking about atoms, I always say atoms, you say atom, I say neutral, talking about atoms are neutral. So they found that the negative part of these neutral compounds, neutral entities or elements, were these small negatively charged particles. They're using those ideas. Any case, as you can see, as maybe intimidating to some people, this question asked for very simple answers. I do not want you to think that part two is harder. Part two in a lot of ways can be easier. Yes, you have to know some things. Yes, you have to be able to put them on paper and not choose. But in this case, some of these questions, for the most part, I would think 67, especially in 66, okay, are reading comprehension questions. And you know, you should already know that atoms are made of protons, which give its positive structure in the nucleus. You should already know that atoms have electrons and negatively charged particles. So do not be intimidated by the information they give you in Part C. You can clearly see the information or what they're asking for is very simplistic. Okay, there's never going to be something very, very, very difficult here. So you just don't get intimidated. Go right to the question. Number 70. So question 70 through 72 is using this little blurb. Okay, and again, I suggest you go right to the question to see what they want you to ask about this blurb. You're reading this blurb, and you know, you may say, oh gosh, I don't know what they're talking about. Don't get yourself all crazy about this information. Go see what they're asking for, because a lot of times, as you're going to find out, the questions are really easy, and sometimes a lot of this information you don't even use. So let's go right to the question. They said, determine the total number of moles of CO2 added to the tank. That's what they want. They want the total number of moles of CO2 added to the tank. So let's go back into the blurb. We need some information. And as I read this, what do I see? I see that 340-gram sample of carbon dioxide is added to the tank. They're giving me 340 grams of carbon dioxide. That's all. And they want to do what? How many, what? Determine the number of moles of it. So given 340 grams of carbon dioxide, they want moles. I think we can do this, right? This is a conversion from grams to moles. It's got really nothing to do with this extra information. That's all they want. Convert your grams to moles. Don't get crazy about this blurb. Let's do that in the answer booklet. Okay, so they gave me 340 grams of CO2, and we got to convert that to moles. So you remember, to do that, what we're going to do is we're going to times it by some kind of factor to get rid of the grams. So using your units I'm going to put the grams on the bottom, and I want moles. I put 1 mole on top. Okay, now I need the converting factor. How many grams equals 1 mole? And you need the gram formula mass. So we're going to have to go to the periodic table to do a gram formula mass to find that number. So we have 1 C and 2 O's. Let's go see the atomic mass of each element. So at the periodic table, I find the atomic masses of each of these carbons, and these are the masses per 1 mole. We're going to round them off because we're going to assume we have the most abundant isotope. So this is going to become carbon 12, and this will be oxygen 16, and these are the masses we're going to use per 1 mole. If I have a mole of carbon, we've made it so that this atomic mass, this relative atomic mass, equals 12 grams. We've made a mole so that the atomic masses are the grams per 1 mole of these. So in CO2, what do we have in the compound? We have per 1 mole of CO2, we have 1 mole of carbon atoms, which is 12 grams, and 2 moles of oxygen atoms, who are 16 grams apiece. Let's go back to the book and find that answer booklet. Let's go back to that and find the formula mass, or molecular mass. So when we have 1 mole of CO2, we have 1 mole of carbon atoms. 1 times the mass of 1 mole of carbon atoms from the periodic table rounded off was 12, so that 1 times 12 is 12. I know my 1 times tables. Then I have, in 1 mole of CO2, I have 2 moles of oxygen atoms. 2 times the mass of 1 mole of oxygen is 16, rounded off, and I get 32, and I get the atomic mass to be 44, the molecular mass to be 44 grams per mole. And that goes here. All right, for 1 mole of this is 44. So we needed the molecular mass. And we've got that. Now we have the converting part. And now we can see that grams cancel. That's why I use my units to convert. Take my calculator, and we just take 340, and we divide by 44. And you get 7.7. We started with 3 sig figs in our conversion. We should end up with 3, so 7.73, and that's moles. And I'll put that right here. They didn't ask for the work, but you know, it's a good habit to show it anyway. All right. Although I'm using the correct number of sig figs, you could have used any incorrect number of sig figs and it would be correct because they didn't ask for it. Okay, unfortunately, but take any number that's close to 7.73. They need to be specific. They'll tell you when, but it's just good practice to do so. Number 71. So the first question was just about converting grams to moles. All right, and number 71, let's see what the next question was about this blurb. In the box in your answer booklet, use the key to draw a particle diagram to represent 2 phases of CO2 in the newly filled tank. Your response must include at least 6 molecules in each phase. You have to pay particular attention to what exactly they're asking for. They're telling you exactly how you should answer. Do not draw 4. Do not draw a 5. At least 6 molecules of each phase. It's so disheartening to grade these regents and see students get it right, but they draw 5. Okay, so you may not know what's going on here, so let's go back into the reading. It says at 20 degrees Celsius, this tank contains both CO2 gas and CO2 liquid. Those are the 2 phases they want you to draw in this tank. Okay, so you have liquid and gas, and you're going to, in the answer booklet, you're going to show me with 6 molecules of each what this would look like. Let's go there. Now, they said in number 71, if you have your test in front of you, in the box in your answer booklet, use the key to draw a particle diagram. Here is the key. This is what a CO2 molecule looks like. So that's just a simple open circle. Try to stay with what they're asking for you to draw the 2 phases of CO2. Okay, well, we have a liquid. Now you should know liquids have higher attractive forces or intermolecular forces of attraction, so they're going to be a more dense phase. So I'm going to draw 6 liquid molecules, not in any kind of regular repeating arrangement. And I'm going to draw a few more because I'm a little bit artistic today. I guess you can draw them different sizes in terms of perspective of how close they are. So there's my liquid. No real organizational pattern, right? Because if you were to draw them in a what? A regular repeating pattern, okay, then you are implying a crystal structure. So liquids do not have a crystalline structure or a regular geometric pattern, but they're going to be closer than the gases. Now the gas in the tank is going to totally fill the open area. So the gases are going to have more distance between themselves because they have higher kinetic energy. So something like that. I drew at least 6 for each. I showed that the liquid, okay, is going to be in close uh, proximity to each other, the liquid phase, because they have high attractive forces. And I showed that the gas is going to fill the rest of the air above it. Gases always fill the container they're in, all right? And it's going to take the shape of the volume there. And of course, there's greater distance between them because gases will have less density. And that's what you needed for that question. All right, so you need to understand the differences between the two phases. Of course, this understanding has nothing really to do with the reading other than them telling you in the reading you had a gas and a liquid phase. So don't be intimidated by these blurbs. 72. Number 72. After the paintball game, the tank has a pressure of 6.1 atmospheres and is at 293 Kelvin. If the tank is heated to 313 Kelvin, the pressure of the tank will change. Show a numerical setup. They just want you to set this up. Show a numerical setup for calculating the pressure of the gas at the new temperature, 313. This is a gas law question, okay? It's just a gas law question. And again, something you've seen before and something we can handle. The blurb, if you were to read this, you may get stuck on 508 cubic centimeters and say, what the heck is that? 508 cubic centimeters has nothing to do with any of these problems. Okay, 508 cubic centimeters, if you remember, is a cm cubed. And I'm just showing you how you can get all caught up with the information they're giving you. They just want you to do and just set up a gas law problem. Okay, if you forget the gas law formula, let's go to table T for a second. So here we are at table T, and let's go find that gas law formula we need if you don't remember, and it's called the combined gas law, and here it is. And real simply, we're going to utilize PV over T, and you have to remember that this works because the moles are constant, and there may be a scenario like this question where when one of the variables stays constant, you can cross it off. In this question, if you have it still out, they're giving you a pressure of 6.1 atmospheres, and it's at 293 Kelvin. The tank is heated to 313. What's really the new pressure? So they're not giving you volume changes here. Okay, so the volume is fixed since they're not giving you a change in volume. So our formula is going to be this, but we're going to basically X out the volume. So we're going to have pressure 1 over pressure 2, or the current condition, over the new pressure over the new temperature, and solve for. We're not going to utilize the volume because it stays constant. How do I know? Well, because they don't give you a new volume. Okay. All right. So we're at the answer booklet here. So we're at the answer booklet, and what we're going to do now is put in our values for the equation. So the equation from table T is as written, P1 over T1 equals P2 over T2. And notice I'm not writing in the volume. All right, now I'm not a big fan of the 1s and the 2s. I always tell my students that this is the current condition, and this is the future. Okay, I'm not sure if I talk like that in the future, but hey, who knows? So, any case, all they have to do for this problem, since they said show a numerical setup, so just plug it in. The initial pressure, the current pressure from your question 72 says that it's 6.1 atmospheres. The current temperature in Kelvin, and it's very nice of them to keep it or have it in Kelvin for you, because if it was not in Kelvin, you'd have to convert to Kelvin. So 293 Kelvin. And they're saying the tank is heated to a new volume of 313 Kelvin. I can do this, 313 Kelvin. And basically show a numerical step calculating the pressure of the gas at this temperature, the new pressure. It could be your P, P2 or X, and this is really all you need, okay? In fact, if you didn't have the units, that would be acceptable to have 6.1 over 293 equals X over 313 or P over 313. So just the setup. I know it seems odd, but they just want the setup. Now, if you calculate the pressure, whether you do it incorrectly or correctly is inconsequential here. They just want the setup. The setup is all they were looking for. Okay. Number 73. This question is in regards to a new little blurb, and this blurb is about, I guess, making bread with yeast. Not really sure, not really caring. Let's go to the question first so I don't get intimidated. Draw a structural formula for the ethanol formed during this reaction. All right, they just want a structural formula. I don't need to understand what this is about. I just need a structural formula for the ethanol. So what is the ethanol? Well, you should know that eth means 2 carbons, okay, right? And ethane means single bonds, and O is an OH group. The bottom line is you're talking about this right here, all right? And if you weren't sure, they said in the problem, glucose, okay, is converted to ethanol and carbon dioxide. So this is clearly carbon dioxide, so this is your ethanol. So they want you to draw a structural formula. All right, let's go to the booklet. All right, so they gave me this, okay, which actually is a structural formula as well, but I guess they want a stick model. So I know that the first carbon is bonded to 3 H's. So I write that. The second carbon is bonded to 2, and it's going to make some sense here because every carbon must make 4 bonds in my drawing. Each dash here is a bond. Then I'm bonded to an O, then to an H. I should put lone pairs here, but they're not necessarily needed. Okay, but the bottom line here is this is what they're looking for. Eth, if you remember, means 2 carbons. And that's from table what? Table P. Ane part means that they're single bonded, if you wanted to go that route. And that's from, this is from table Q. And the OL part, that means you have an alcohol or a hydroxyl group. And that's from also another table that you need, table R. So you could have worked that out as well using your reference tables. P, Q, and R are your friends when it comes to building the formulas or structural formulas or naming these functional group type of organic compounds. In any case, here we have to understand that carbon makes 4 bonds, and this pretty much lays it out exactly how you have to show the bonding. Oxygen makes 2 because it has 6 valence electrons, and again it should make some sense what's going on here. Number 73. So let's go to 74 now. Okay, so now we're working on 74 here, which is another question based on the blurb, but interesting enough, look at the question. Describe how the catalyst zymase speeds up this reaction. Well, okay, it's interesting blurb, but as you can see from 73, drawing a structural formula had nothing to do with this information, and you should know how a catalyst speeds up the rate of reaction, right? How does a catalyst do that? If you remember, catalysts, if you look at a potential energy curve, they change the pathway. There's an alternative pathway here, as I probably should do in a different color. The pathway is an alternative in a way that it lowers the activation energy. The energy needed to do what? Start the reaction. So my friends in chemistry, this is just a question regarding, did you know that the catalyst speeds up a reaction rate because it lowers activation or has an alternative pathway? This is something you should already know. It has really nothing to do with this, and that's why you don't get intimidated by these blurbs, and that's why you go right to the question. So go to 74, please. The answer booklet. So I wrote in the answer booklet, a catalyst decreases the activation energy, or it provides an alternative pathway that requires less energy. This is a major piece of information that you should have already from your course. If not, get it down. A catalyst lowers the activation energy. Whether you're looking at a potential energy diagram, or they ask you to write it in part 2, or they do what? Ask you to write it in a multiple choice section. This activation energy is the energy it takes to get to the top of the hill. When you add a catalyst, it makes a new pathway that's lower in energy, and this activation energy is dropped. Okay? Very important concept that's going to be somewhere in your test, multiple choice or part 2. In this case, it was part 2, number 75. So number 75, okay? Determine the total mass of ethanol that we have just established is this molecule, produced when 270 grams of glucose, okay, 270 grams of glucose, that's this chemical that I know from previous understanding of chemistry. I have some, I guess, but I also know in the reading, if I go back into the reading, and again, I say don't read the blurb, but if you have to go back and see what things are, what some hints are, go back. Okay, so the glucose clearly is the C6H12O6, and we have 270 grams of it. And it reacts completely. All of this disappears to form your products, to form ethanol and 132 grams of carbon dioxide. So they want the mass of the ethanol. If I know the total mass of my what? Total mass of my reactants to be 270, and I know that my products, part of my products is 132, can I figure out exactly how much ethanol? Yes, you bet your donkey you can. All right, because the total mass of the reactants have to equal the total mass of the products. This is the law of conservation of mass. This is what balancing chemical formulas is all about. So 270 grams of your reactants have to equal 270 grams of your product. So all you have to do is subtract these two values to get the difference, which has to be the ethanol. If you don't understand that, if 270 grams of the reactants totally gets reacted, that means all of these atoms and all of their mass associated with them is now distributed somewhere in the product side. If I know part of their mass is 132, then the rest of the missing mass has to be 132 subtracted from 270 to get the mass of the ethanol. All you're doing is subtracting. Now, for those that had a higher level chemistry class, could you convert this to moles and do a stoichiometric problem and find the moles and convert back to grams? Sure, but you're doing a lot more work here. That's not what they're after in this question. They're after, can you see the law of conservation of mass? Let's go to the answer booklet. So back to the answer booklet here. I take my 270, I subtract from 132, and I get 138 grams. Okay, not a big deal. Again, these three questions from this blurb were very, very simple in their design and what they asked, what they wanted you to solve for. So you have to look at it that way. Don't say, my gosh, what am I looking at? This is so difficult. No, they're looking for something very simple in design, kind of using that paragraph. You've got to think that way. Number 76. Number 76, we have a brand new blurb that goes with these four questions, okay? We're not intimidated. We're going to go right to the questions first. What number of significant figures is used to express the concentration of the KOH? So the concentration of the KOH, concentration is molarity, part per million. So I'm going to find the KOH, and there it is. I have to go back into the blurb. I got to look back and see what information's there I can use, and there's my number. It's 0.150. Okay, they want significant figures. So this question has nothing to do really with anything in terms of what this is saying, other than from this number, how many sig figs are there? Okay, and we have four basic rules. Okay, the first one is that all all non-zero numbers, so anything that's not a zero is significant always. Okay, that's the first rule. So far we have two. So the first rule is all non-zero numbers are significant. All right, second rule. All right, any sandwich zeros are significant. Now a sandwich zero would be like a 101. If this 0 is sandwiched in between two non-zero numbers, that would be significant. We don't have any sandwiched zeros here, so that doesn't come into play. So the next rule would be leading zeros. Leading zeros are never significant, okay? Because all they are placeholders and they don't help us out. For instance, 0.000013. All of these leading zeros are placeholders that help us get out to this very small number. If this is, and so these two would be only significant. So leading zeros are never significant. So we're down to this last 0. The fourth rule, if you remember back in September we did this, the fourth rule states that ending zeros are significant only when a decimal point is present. For instance, if I had 1300 meters, these zeros are not significant if there's no decimal point. They're just placeholders that help me get out to this big number. So if I had 1300 meters with a decimal point, these zeros were measured and they are from a measurement device and therefore they're significant. So leading zeros aren't significant, but ending zeros count if there's a decimal point present. Well, we have a decimal point present, so this 0 is significant, and we would have 3 significant numbers for number 76. So 3 significant numbers. Number 77. 77, complete the equation in your answer booklet for the neutralization reaction. Okay, we should remember that a neutralization reaction is an acid and a base, makes salt and water. Remember the demonstration that I talked about? Had the strong acid, the strong base, I stirred it and I drank it. I was drinking salt water. That occurs during the titration. So you have a titration going on here, but they said complete the equation in your answer booklet, so let's go there. So back at the answer booklet, I see that my equation's written for me. These are the reactants. They want you to complete it. As you can see, did I need the blurb at all to do this? No. In fact, they just said we could have done these two questions independently of that blurb. So again, look at your questions first. So we have to realize what kind of reaction we have. We have a neutralization reaction, but we have to realize that we're really dealing with a double replacement. K likes to become +1. I like to split my positives and negatives. Hydroxide's -1. The proton in this acid becomes +1. Cl is -1. So what's going to happen is the partners are going to double replace. This positive is going to hook up with this negative. So we're going to have K plus and Cl negative, so that makes KCl. Don't just blindly push these together when you do double replacements. You have to consider the charges. If K is +1 and Cl is -1, and if you're not sure, you can go to the reference table, the periodic table specifically, and look at the upper right hand corner to see what their charges are, and make sure you make a neutral compound. In this case, the K happens to be +1, Cl is -1, so my friends in chemistry, that these guys come together in a 1-to-1 format. Then you have the +1 of a proton with the hydroxide who is -1. All right, and if you're not aware of those charges, you can go to table E to see that a hydroxide is -1, but you make HOH. Now I tell my students to write HOH so you can see that an H comes to that, but you could have write H2O for water. Okay, so it's just a double replacement reaction, and just make sure that you have the right formula of the salt written here. In this case, it's a 1-to-1 and very easy. Now I would also make sure that you're balanced. Okay. And we are currently balanced, so it really wasn't about that. But if you're not sure, 1K, 1K. All right, 1 hydroxide, 1 hydroxide. Okay, 1H outside of a hydroxide, 1H, 1Cl if you want to look at it that way. We should have the same Same mass and same mass on both sides because of the law of conservation of mass, but we should have the same number and same type of atoms on both sides, and we do here. Number 78. So number 78 says determine the concentration. They want the concentration of the hydrochloric acid using the titration data that has to be in the blurb. So now we really got to go in and see what's going on here, okay, in this question. But they want the concentration of the HCl. So during the laboratory activity, student places 250 milliliters of my acid. So there's the information of my acid. of an unknown concentration in a flask. You probably did this. You should have done this lab in your class. Okay, it's very important. Student adds 4 drops of phenolphthalein to the solution in the flask. The solution is titrated with a base, a known concentration, until a faint pink, persists, I should say. The volume of the base that you added from your burette is 18.5. So you probably had this scenario in your class. You had a burette, which is an emptying device, probably not crooked like mine is, and inside that you had your what? You have your KOH. That's your standard solution. It's a solution you know about. Its molarity is 0.150 molar. And down here you have your acid with your phenolphthalein, and you have your HCl of unknown concentration, but you know how much you started with, which was 25 milliliters. Okay, so you're dropping drops of Jupiter, or at least drops of base hydroxide, and you keep adding what? Hydroxide until you what? You neutralize, and the phenolphthalein is going to tell you. So what this is all about is we're matching, okay, hydroxides, we're dropping hydroxides from the base to neutralize the H pluses in the acid to make water. And we're going to keep adding the base until we neutralize it. And the phenolphthalein will tell us approximately when we have reached the stoichiometric endpoint, or the endpoint of the titration. So we use a formula to do this, to match H pluses that equal each other. And the formula we use is the MV of the acid equals the MV of the base. And we get that from table T. So here I'm at table T, and here is my titration formula. And there it is, my molarity of my acid times the volume of my acid equals the molarity of the base times the volume of base. So it's right there if you forget. And of course, the reason why this works is because you're matching the moles of the proton with the moles of the hydroxide. Okay, and that's what that's about. So let's go to our answer booklet and plug these values in and solve for it. So right from table T, I'm going to write molarity of my acid, volume of my acid equals the molarity of my base times the volume of my base. My acid is HCl and my base is NaOH. What values did they give me in the problem? Looking at your test, you should see that they said they want the concentration of the HCl. So this is going to be our unknown. We could leave it as M, but we'll just put it as X. People are more comfortable with the unknown being X. What's our volume of our acid? In the problem, they said there was 25 milliliters. Okay. And what we're going to do is we're going to set this equal to, because really this is moles of acid equals moles of base. And the molarity of our standard solution is 0.150 molar. And the volume that we needed to neutralize was 18.5. So now we're going to solve for X. So this becomes 0.150 times 18.5 divided by 25. And that's going to solve for the molarity. All right, take your handy dandy calculator. 0.150 times 18.5 divided by 25. And I get a molarity that's equal to 0.111. Okay, so the molarity is 0.111. All right, so that's our molarity. If you don't have the 0 in front, it still work. Also, if you don't have the right number of sig figs, they will not take off. So if you had 0.1, 0.11, 0.111, okay, any combination that is approximately the right answer there would be acceptable. Okay, they didn't say to the correct number of sig figs, unfortunately. Number 79. So number 79 says, describe one laboratory safety procedure that should be used if a drop of KOH is spilled on the arm of a student. Okay, so if a drop can be spilled, okay, so what would happen here? Well, let's go to the answer booklet. because this question really has nothing to do with the blurb. The blurb doesn't talk about safety procedures. It's something that you should already have talked about in your classroom and gone through, and it'd be signed a safety contract. So this is really a general question of your knowledge of safety procedures in the classroom that you're being tested on here. So again, the blurb had very little to do with a lot of these questions. And again, we don't get intimidated. Let's go to 79's answer booklet. So just use your common knowledge of safety procedures. The first thing you probably have learned that if there's something happens in the laboratory, notify the teacher, number one. Certainly could say, have the student place their arm under running water to dilute and wash away. A whole host of other possibilities that make any kind of common sense towards safety procedures or correct safety procedures would be acceptable here. Number 80. Okay, 80 to 82 has a brand new blurb, and let's go to the question first. Number 80, state the direction of heat flow that occurs between dry ice and the air in the flask. Okay, so we need to go into the blurb to see what the temperature is, because we know that heat flows always from hot to cold. That's the point. That is what this question is getting to in terms of it's testing your basic understanding of thermodynamics here. So let's see what the temperature is. So we have the dry ice at negative 78, so that's very cold, and it's placed in a flask that contains air at 21 degrees Celsius. Clearly, the air temperature is warmer than the dry ice. Okay? So clearly, heat's going to flow from the higher temperature to the cold, from the air to the dry ice. Let's go to the answer booklet. So the heat flows from the air to the dry ice, as we said, and it goes from hot to cold, from the warmer temperature to the colder temperature. Number 81. So 81 states, write the name of the process that occurs as the dry ice undergoes a phase change in the flask. So you need to understand what dry ice is doing. Let's go back into the blurb to see if they give us any hints. Dry ice is -8 placed in a flask. The flask is sealed by placing an uninflated balloon over the mouth. As the balloon inflates, the dry ice disappears and no liquid is observed. So we had an uninflated balloon over the flask over the opening of the flask. So we had like an Erlenmeyer flask. We had some pieces of dry ice. All right, notice it said solid CO2. So we had solid CO2. We had this, let's make it a balloon that's attached to the flask of the balloon here, top of the flask. It was uninflated. As the balloon inflates, so now the balloon's getting bigger, okay, it's expanding, there must be gas being made. So the solid must be turning into a gas to inflate the balloon. So what they're looking for is they want the name of the process or the phase change where a solid goes directly to a gas. And that is what they're after in this question. And of course, the name of a solid going to a gas is sublimation. So sublimation is the phase change of a solid going directly to a gas, skipping the liquid phase. That's why they call it dry ice. There's no liquid involved as it sublimes. You should be aware, though, if I can go from a gas back to a solid, they call that deposition. We mentioned that somewhere in the test in this review. Number 82. So number 82 states, compare the entropy of the CO2 molecules in the dry ice, which we know is the solid. So we're comparing the solid to the entropy of the CO2 in the inflated balloon. Well, we have to know that in the inflated balloon, we're dealing with a gas. So how do we compare a solid to a gas? Well, a solid has a regular repeating arrangement called a crystalline structure, okay? Whereas a gas has no organizational patterns whatsoever. Their gas molecules have more kinetic energy and are not locked in a fixed position. So clearly, as we go from a solid to a gas, as I like to say, the amount of disorder is increasing. And entropy is a measure of chaos or disorder. So we can see that the entropy or the disorder or the chaos clearly is increasing as a solid who can only vibrate in its fixed position changes into gas molecules who can fly around the room at hundreds of miles an hour. So you had to know for this question what entropy was. And you needed to know for this question, as we go from a solid to a liquid to a gas, the amount of disorder increases. And if you go from a gas to a liquid to a solid, your disorder would decrease as you become more ordered. So this question was clearly about the idea that your disorder was increasing as you become a gas. So I said the CO2 molecules in the dry ice have less entropy, than the CO2 molecules in an inflated balloon. Many ways to say this. Bottom line is the gas is more disordered than the solid. Therefore, the entropy, which is a measure of disorder, is increased as you go from solid to a gas. Okay, number 83. Number 83. Okay, we've got a last blurb here. Let's go to the question. State in terms of neutrons. Ooh, very important that we answer exactly how they want us to. So state in terms of neutron how an atom of tritium differs from an atom hydrogen 1. So you have to go back into the reading and see what tritium is all about. So I'm talking about illuminated signs. Signs may contain the radioisotope tritium hydrogen 3. So the question really states, state how hydrogen 3 differs from hydrogen 1. Tritium is hydrogen 3. So how the neutrons different? Okay, what we need to understand that this is called an isotope. Same element, therefore same number of protons. So this number down here is a 1. You don't see it written. You don't ever say hydrogen 1 because the symbol, okay, is indicative of that number. There's no other symbol other than an H do you give to any other element who has 1 proton. This is unique. The proton number, this bottom number, is unique to the H. So we don't normally write it. H is good enough. It implies the 1. But what you should know is the top number is the mass number. Okay? And you should know the mass number includes what? It includes protons and neutrons. Both of these have mass in the atom. Electrons have mass too, but they're so tiny their mass is insignificant. The bottom number, as I just mentioned, is the proton number. So all you have to do is subtract the proton and neutron number, or take this, I should really say, subtract the proton number, the atomic number, from the proton and neutron number, which is the mass number, and you will get neutrons. Okay? So if you subtract these numbers, the protons cancel. So you should remember 3 minus what? 1 gives me hydrogen 3 to have 2 neutrons. Tritium has 2 neutrons. Hydrogen 1, 1 minus 1 gives me 0 neutrons. So in terms of neutrons, tritium, H3, has 2 more neutrons than hydrogen. Okay, now if you forgot that the mass number is protons and neutrons, there's a place to look, and I want to go there because it's a very underutilized reference table. If you've been with me through the entire test, you know table S is the most underutilized, but this I would say is second place. Let's go to table O. All right, so the point of table O is to find out who has the mass in the atom, or remind myself that neutrons and protons make up the mass of the atom. So here's a neutron. Look at the top number. It's the mass number. It's a mass of 1. Here's a proton. Whether you use an H or a P, is a mass number of 1. Now you may say, well, where's the electron? Well, electron is the same as a beta particle, believe it or not. And that is a mass of, well, they put a 0 here, but it's insignificant compared to the others. So everyone else, okay, that's a subatomic particle, is a 0. So it's the neutron and proton that give the mass of the element. That's one way to remind yourself. But clearly, let's go back to the So let's go back to the answer booklet. So 83, a tritium atom has 2 neutrons and an H atom has no neutrons. Again, you should understand that to get neutrons, whether it's this problem or any other problem, you're taking the mass number and the proton number, you subtract them, and you get your value for neutrons. In this case, this second one was 1 minus 1 was 0. So it's a skill that will come up in other tests. This time it came up in the part 2. So 84, determine the fraction of the original sample of tritium that remains unchanged after this amount of time. So this is essentially a half-life problem, okay? And we need to know what its half-life is. So this is the total time. To do these types of half-life problems, I've always preached, draw yourself a table. So I'm going to make some room for myself here, okay? And I'm going to need some information. We'll get there as we go. But here's my table that I draw for all of these types of half-life problems, where we know that we're going to be halving and trying to figure out what's remaining. You should be able to identify these questions. So let's do that. So I draw myself a 0 line in the beginning. This is a 0 timeline. There's 0 time. There's 0 half-lives. Now, half-life is the amount of time it takes for half of the substance to decay into something stable. So 0 time. And this would be 100% of my substance. We're assuming it hasn't decayed yet. Now, 100% is the same thing as 1 over 1. Okay. Now, what did they give me? They gave me the total time to be 24.62 years. Now, for me to figure out how many halvings have occurred, how many half-life periods, I need some information. I need to know what the half-life is, so I go to table N. Table N. Na, hey, table N, let's go. So here's our table N, selected radioisotopes. These are the isotopes of some elements that are radioactive. They have an unstable nucleus, and let's go find our element that we're talking about. In this case, the hydrogen, the isotope of hydrogen that is radioactive. And here's our tritium, H3. Notice they don't need the 1 there. The H implies the 1. And look at our half-life, 12.31 years. This tells us what kind of particle it likes to give off. It's a beta particle, okay? But that doesn't matter. We need the half-life period, 12.31. All right, knowing the half-life period is 12.31, I'm going to find out exactly how many halvings have occurred. So knowing that total time is 24.62, and each half-life from table N is 12.31 years, clearly, when I divide these two numbers, I get 2 half-lives. 2 halvings have occurred. So the first half-life, time was 12.31. Now I have, first halving is 50% of my sample, which is 1 half. The second half-life, I add another 12.31 time, which is 24.62. Now I take a half of 50%, and now I have 25% of the original sample. And of course, a half is a quarter. And that is my answer. The answer is 1/4 of the original sample is remaining. So we say 1/4 is remaining. And there's nothing more difficult. You can say 0.25 or 25%, all the same to the Regents and me. So number 85, last question. Number 85, complete the nuclear equation in your answer booklet for the radioactive decay of tritium by writing a notation for the missing product. So let's go to the answer booklet. Okay, well, let's get this little bigger here so we can see what's going on. And we're going to finish this decay. Now, this is called natural transmutation because by itself, okay, you're going to see tritium get its nucleus stable by giving off this beta particle. They were very nice in giving us the beta particle, but there could be other questions where they wanted you to figure out what particle it was. Now, we just went to table N, and we saw that B negative was one of the decay products, okay? And if you go to table O, it'll tell you that that's the decay product. Now, in this question, they gave you that it was a beta particle being emitted. So all we have to do here is match up the charges and mass on both sides. It's total mass of 3 on the reactant side. We need a total of 3 for a mass on the product side. So what number plus 0 is 3? That would give me a 3. Okay? Now we have to have the same mass of charge be conserved on both sides. This is a plus 1. This is a negative 1. Okay? So what does that mean? So I need some number on the bottom, which is the charge number, the proton number, plus a negative 1 that gives me 1. What number plus a negative 1 gives me 1? And that would be 2. Now we're not done, because we have to say what chemical symbol is this? What chemical symbol has 2 protons? If you're not sure, you have to go to the periodic table. So as we can see, helium is going to be the symbol that we put into the notation because it's the only element with atomic number 2. So back to the notation. So we write He. Can't say how many times I've seen this question. Not very difficult. Conservation of what? Conservation of mass for the top numbers, conservation of charge on both sides. I've seen so many people get this wrong because they put the wrong element here or they forget it. Okay, now certainly you could write it different ways. You could write it helium 3. You could put He3, because again, what did I say before? The bottom number, okay, is implied with the symbol, but I tend to write this because what we're doing here is we're trying to figure out what 2 numbers add together on this side equal this number, and what 2 numbers on this side equal this number. That's what I'm doing here. Okay, so that concludes the test, the free response section. I hope that helped.